Why does lightning look like wild chaos in the sky, yet always seem to know exactly where to go? At first glance, it seems like a random scribble drawn by a child with a glowing pen, darting left, right, and splitting into forks for no reason. But here's the twist. Lightning is not random at all. Every jagged line is the product of strict physical rules. It's a map of resistance, a natural algorithm searching for the easiest path through the air. And once you see how this works, you'll never look at a thunderstorm the same way again. Let's start with what looks obvious. A lightning bolt is electricity leaping from one place to another, usually from cloud to ground, sometimes from cloud to cloud, or even from ground back upward. If electricity wants to move, why doesn't it take the shortest route, a straight line? Why all the zigzags? The answer lies in the invisible structure of the air itself. The sky above us looks empty, but it's not. It's full of molecules, tiny variations in temperature, humidity, and pressure, and all of these influence the path electricity will take. Here's the analogy that makes sense of it. Imagine you're running downhill in the dark, holding a lantern that only lights a few feet ahead. You want to reach the bottom as fast as possible, but you can't see the whole slope at once. Instead, you make little choices at every step. Turn left where the ground feels smoother, bend right to avoid a rock. Step by step, you trace a path of least resistance. That's exactly what lightning does. It doesn't draw one big zigzag at once. It builds itself forward in tiny invisible steps, hunting for easier channels through the atmosphere. Scientists call these steps leaders. Before the brilliant flash you see, an invisible finger of charged particles creeps down from the cloud in small jumps, each about 50 meters long. This leader branches and probes, like roots searching for cracks in the soil. The air is not uniform. Some patches are more humid, some denser, some thinner. Electricity senses these differences, and the leader always prefers the easier route, where resistance is lower. By the time the lightning becomes visible, the path is already chosen. The giant bolt you see is just a flood of energy racing down the trail that the leader carefully scouted. This means every lightning strike is actually two events. First, the invisible search, then the blinding flash. Think of it like a race car driver walking the track before the big race. The scouting lap doesn't get much attention, but it decides everything. When the actual lap begins, the driver already knows where to go. Lightning works the same way. First the invisible lap, then the main event. Now here comes the part that feels almost artistic. When the leader branches, many paths start forming, but not all survive. The branches that find easier air continue, while the others fade away. It's natural selection at the speed of light. Only the strongest, most conductive path makes it all the way down. That's why a lightning bolt looks like a tree in the sky. Countless trial branches, but only one trunk carrying the main current. Let's zoom in even further. Why do these leaders form in the first place? It begins with the buildup of charge inside a thundercloud. Turbulent winds toss ice crystals and droplets around, separating positive and negative charges like someone shuffling a giant cosmic battery. Eventually, the difference in charge between the cloud and the ground becomes enormous, millions of volts. The air in between is normally an insulator, blocking electricity. But when the stress is high enough, the air itself begins to break down. Molecules split, electrons escape, and suddenly a channel of ionized gas appears. That's the leader, a tunnel of weakened resistance that electricity can exploit. Here's a vivid picture. Think of air as a brick wall and electricity as a person trying to break through. Normally, the wall is too strong, but under high tension, cracks begin to form. The person doesn't smash through the entire wall at once. They look for cracks and push where the mortar is weakest. The path of least resistance emerges piece by piece, and when enough cracks align, the whole wall collapses in a dramatic rush. That collapse is the flash of lightning. And notice something else. Lightning doesn't only come from the clouds. Sometimes streamers of charge rise from the ground to meet the descending leader. Trees, buildings, even people can emit these invisible tendrils of charge upward. When one of them connects with the descending branch, the circuit closes, and the main bolt follows instantly. In other words, the ground often reaches up to meet the lightning halfway. That's why tall objects are so vulnerable. They don't attract lightning magically, but they make it easier for the connection to happen. What about the speed? Lightning seems instantaneous, but in reality, the leader crawls downward at about 200,000 kilometers per hour. That's fast, but not light speed. The final return stroke, the brilliant flash, is much faster. It races up the leader's channel at about 1/3 the speed of light. That's why we see lightning in one explosive blink. The slow buildup is invisible, and the payoff is dazzling. Here's where the eureka comes in. Lightning isn't a chaotic scribble, it's a negotiation between nature's forces. The bolt you see is the final signature of that negotiation, a glowing line that reveals how the atmosphere offered resistance and how electricity overcame it. It's not random, it's a map of the invisible structure of the sky at that exact moment. Each jagged bend is an answer to a hidden question: where is the easier way forward? And here's a surprising thought. If we could record every lightning strike in the same spot over years, we'd build up an electrical fingerprint of that place. Each bolt would be different, but together they'd reveal the unique microstructure of the air currents, humidity, and terrain beneath. Lightning is like the handwriting of storms, scribbling notes about the hidden physics of the sky. When you see a bolt split into forks, you're not watching chaos, you're watching a competition. Dozens of branches race outward, probing for paths. Only one wins the prize, becoming the main channel of discharge. The others vanish like sketches erased from a notebook. This is why lightning feels alive, like a decision-making creature. But it's not life. It's physics running its course, faster than the eye can follow. Even sound plays a role here. That deafening thunder that follows the flash, it's the echo of air being torn apart. When electricity surges through the ionized channel, it heats the air to 30,000 degrees Celsius in less than a millisecond. That's 5 times hotter than the surface of the sun. The air expands violently, producing a shock wave that we hear as thunder. The crooked path of lightning actually shapes the crackling sound. It's not a single boom, but a rolling series of echoes, as each kink in the bolt creates its own sonic burst. Think about this. Every time lightning strikes, it is redrawing a map of the sky's hidden resistance. We see only the glowing ink, not the invisible drafting process. But once you know the secret, every zigzag makes sense. The bolt is not wandering, it is navigating, solving a puzzle in real time. And the solution is written in fire across the sky. And here's something even more mind-bending. Scientists studying lightning have noticed that the branching patterns closely resemble fractals, self-similar structures that repeat at different scales, like the veins of leaves, the branching of rivers, or the neurons in your brain. It's as if nature uses the same algorithm to solve problems everywhere. Whether it's moving water, electricity, or information, the path is always optimized by branching and pruning. Lightning is not just weather, it's a glimpse into the universal language of patterns. Now imagine pausing time in the middle of a thunderstorm. You'd see invisible leaders creeping down, probing like curious fingers. You'd see upward streamers rising from rooftops and trees, reaching desperately into the storm. You'd see branches competing, merging, fading. And then, in an instant, the connection is made, and the entire system releases its energy in a blinding flash. What looks like chaos is actually the choreography of physics. The more you look at it, the more elegant it becomes. Lightning isn't just a dangerous flash, it's a message from the sky, a glowing signature of how electricity and air negotiate their differences. And once you know that, the next time you see a storm, you won't just be watching flashes. You'll be reading maps written in light of how nature itself solves the problem of connection. But let's not stop at the science of storms. There's something profound hidden in the way lightning finds its path. It's a natural demonstration of optimization, of how systems choose efficiency even in chaos. The bolt doesn't waste time carving through thick, resistant air. It hunts and probes until it discovers shortcuts. In a sense, lightning is nature running an algorithm, like water flowing downhill or roots spreading through soil. Each fork, each bend, is the sky solving a puzzle in real time. This also means that every lightning strike is unique. Even if you stand in the same field during 2 storms, the bolts won't copy each other. The microstructure of the air is always changing. Tiny eddies, invisible dust, gradients of humidity. All these variables combine into a one-time only set of conditions. The lightning you see exists only once in the entire history of the universe, never to be repeated. It's like watching nature sign its name on the sky with a stroke that can't be forged. And yet, within this uniqueness, there's an underlying rule. The path of least resistance always wins. That's why lightning tends to strike tall buildings, trees, or mountain peaks. Not because they magically attract lightning, but because they shorten the distance, offering a clearer and easier connection. Think of it like cutting across a corner instead of walking around the block. Electricity takes the shortcut every time. This principle is so universal that we see it everywhere. Rivers meander across landscapes not randomly, but by seeking the easiest slope. Neurons in your brain grow connections not arbitrarily, but along routes of least resistance. Even the cracks in drying mud form branching patterns almost identical to lightning. It's all the same story. Energy moving efficiently through a medium, revealing hidden maps of weakness and flow. Lightning just makes it visible in the most spectacular way possible. Now here's an image that might change the way you feel about storms. Imagine the atmosphere above you as a vast invisible maze. At any moment during a thunderstorm, billions of potential paths exist. The leader steps are like a blindfolded explorer with a lantern, testing corridors one by one. Each test changes the probability landscape until the explorer stumbles into a path that reaches all the way down to the ground. And when that happens, the rest of the maze lights up instantly. What looked like chaos is actually a search and find process, written in electrical fire. Even the sound of thunder, that rolling, cracking echo, carries information about the path. A long, jagged bolt makes thunder that rumbles for seconds as different sections echo at slightly different times. A short, straight strike makes a sharper, quicker boom. So when you hear thunder, you're not just hearing noise. You're listening to the three-dimensional geometry of a lightning bolt being translated into sound. It's like a drum solo performed by the atmosphere itself. This connection between form and sound is one of those wow moments. The crooked line you see, the deafening roar you hear, they are two sides of the same event. One is a map of resistance, the other is the soundtrack of that map being burned into existence. It's a symphony of physics, and every storm writes its own score. And what about safety? Understanding why lightning finds its path also explains how we protect ourselves from it. A lightning rod doesn't attract bolts in a magical way. It simply provides the easiest path to ground, a low-resistance shortcut. The bolt chooses it because physics dictates it will. The rod is just an artificial branch in the tree of options, one designed by humans to take the hits safely instead of us. It's a brilliant example of working with physics rather than against it. Now take a step back and think about the bigger picture. Lightning is electricity solving a puzzle in the sky, but the idea scales far beyond storms. It's a reminder that the universe itself is never random noise. Patterns hide beneath the chaos, and if we look closely enough, we find them. From the veins in leaves to the branching of rivers, from the firing of neurons to the crack of thunder, nature keeps whispering the same message. Efficiency hides in complexity. The real magic of lightning isn't just that it lights up the sky, it's that it shows us how the invisible becomes visible. It's a map drawn in fire, a pattern that exists only for a fraction of a second but reveals laws that apply everywhere. Every time a storm flashes overhead, it's like the universe holding up a glowing sign that says, "Look, this is how I work." So next time you watch a thunderstorm, don't just see a dangerous flash, see a story unfolding. See invisible leaders reaching out, branching, competing. See the air negotiating with electricity, shaping a path through resistance. See the ground rising to meet the sky halfway. And when the final stroke blazes across the clouds, realize you're witnessing physics in its purest, most spectacular form. Lightning is not chaos, it is choreography. It is not random, it is reason written in light. And the next time you hear thunder rumble after a jagged strike, you'll know you're listening to the sound of the sky's hidden architecture revealing itself. If this journey through the hidden rules of lightning sparked a sense of wonder in you, imagine what else is waiting to be uncovered. That's exactly what we do here on How It Actually Works. We take what looks like chaos and reveal the order hiding inside. So hit like, share this video with someone who loves storms, and subscribe for more. Together, we'll keep turning flashes of confusion into sparks of clarity.